just throw up a link to some more of the Microsoft quantum stuff up there. None of what I'll be talking about is on there, though. So we're going to be talking about problems in combinatorial optimization. And I want to talk about exact optimization, not approximate optimization. You're given some combinatorial optimization problem. You want to really find the optimum of it. And the class of problems I'll be talking about, and the algorithm could potentially be used for a more general class, but the analysis is a little simpler for this, is so-called Max, I might need to get a better chalk, Max-D Lin 2, sometimes Max-K Lin 2. What are these? These are problems where you have a bunch of variables, z sub I. Try and get a better marker that's a little bit more solid color here. You have variable z sub I. How's that? Is that a little better? Yep. And each of them is going to be -1 or +1, and this I goes from 1 up to n, so just a bunch of binary variables. And you have some objective function that I'm going to write h sub z. And the objective function is going to be a sum of monomials of degree d. So in the case d equals 2, for example, it would be some of like sum over ij, jij, where jij is a matrix zi, zj. So this would be the case d equals 2. In the case d equals 3, you would have terms zi, zj, zk, zi, zj, zk, zl for d equals 4, and so on. And the jij would be some weight. So this may be a weighted problem. So let me just say what's known. Classically, essentially nothing is known faster than brute force as a classical algorithm. So brute force would take a time O star, meaning up to some logarithmic factors, which in this case will be polynomials of n, O star of 2 to the n. That's basically the fastest classical algorithm known that works in general. For the case d equals 2, there is a very nice algorithm due to Ryan Williams that takes time 2 to the omega of n, but it takes exponential space, where omega is the matrix multiplication exponent. I'll ignore that. Basically, you can't beat brute force classically. So quantumly, what can you do? Well, quantumly, of course, you can do a Grover search and speed that up both to.
Wait, sorry. It takes what time again? 2 to the omega?
2 to the omega of n. There's an algorithm that takes 2 to the omega of n, where omega is the matrix multiplication exponent, just for the case d equals 2, and it takes exponential space.
What do you mean by omega of n? Right?
Oh, omega n. Oh, 2 to the omega n. So. Oh, sorry, omega over 3n. Sorry, to the omega over 3n. Sorry about that. Sorry about that. Of course, that would be worse. To the omega over 3n. So, yeah, sorry. So it's a little bit faster, yes. And it's to the omega over 3n. Anyway, that's a side remark, so you don't really need to worry about it. To the omega over 3n. Takes exponential space, and it's only for d equals 2. So for general d, there's nothing known faster than this. And if you want polynomial space, there's nothing known faster than that. And that Williams algorithm is not known how to quantumly speed it up also.
Sorry. 2 to the n over 2 is what?
Okay, so this would be Grover. This would be Grover. 2 to the n would be classical. And then there's a 2 to the omega n over 3 just for d equals 2. But I'm just mentioning it for completeness, but don't worry about it. Nothing is known about how to do it quantumly, and it's also an exponential space algorithm. So that's the best we know.
Schoning and stuff like that doesn't work?
So Schoning is for does not help, no, as far as I can tell. I mean, so the standard form of Schoning is for K-sat, where you're trying to find something that satisfies all the clauses. And here, we're looking for max, so we're looking for a maximum number. You don't know how many, and many of them will be violated. Now, there is a variation of Schoning, which will work for this. But as far as I can tell, I mean, it was only studied to how well can it approximate things which are not exact things. As far as I can tell from putting the details of the paper, it does not give anything non-trivial in this case either. In fact, it doesn't even give a non-trivial 2 to the n minus anything interesting. Like, there's no 2 to the n minus little o of n that's interesting even. Just doesn't, as far as I can tell, but I may be wrong. That's just based on me reading a subsequent paper after Schoning. So this is the best we know how to do classically. Quantumly, you can ask what you know how to do quantumly. And so classically, of course, let me emphasize, there are lots of heuristic algorithms that in practice do way faster than this for many important instances, but that's the best provable. Quantumly, people have studied a heuristic, the adiabatic algorithm, which would consist of studying a family of Hamiltonians. So you would have h, which would be some h of z, we'll write as s h of z plus 1 minus s x, where x is the sum of the terms xi on each spin. It's a transverse field. And you might imagine varying this s from 0 to 1. And at s equals 0, 1 minus s, sorry, s equals 0, this term is the dominant term, and you can easily prepare the ground state. And you guess, well, maybe there's no closing of the gap. No, the gap never becomes too small along the path. And then you could prepare the ground state. Unfortunately, I think the situation is even worse for this algorithm. That is, not only are there no provable guarantees, I think there's a lot of evidence that in practice on really generic instances, it's super exponentially slow, that the gaps will become n to the minus n small, super exponentially small gaps, and that's how long it will take. So I don't think, it's really even a useful heuristic. So that's kind of the situation. And I want to talk about more about why, my interpretation as to why it takes that long. And I want to apologize a little bit to the next speaker because I saw there's going to be something in there. And there's a statement that I think in the next speaker's abstract that maybe one problem is that this Hamiltonian has no sign problem, or as they say now, stochastic sometimes, that so okay, so there should be a minus sign in front of here, sorry, if we're going to minimize the energy. That I don't think that's a problem at all. I think the problem with the adiabatic algorithm is, I don't know if that's what the next speaker speaks. The next speaker was just saying that that's a common belief. But okay, good. So there's a paper by Altshuler and company in condensed matter physicists talking about a problem with this algorithm based on many body localization. And the idea that they say is the problem is this. They say, okay, let's look near s equals 1. So we've got a small transverse field. And so now you think about the Boolean hypercube. So I'll just draw a small Boolean hypercube, right? So we'll draw a little tiny cube like this. And somewhere, here's the ground state wave function. Here's the exact ground state of the combinatorial optimization problem we want to study. And as you turn on this transverse field, the wave function sort of, instead of being peaked here, it gets some amplitude that spreads out across the cube. Of course, I'm drawing this kind of very, very loosely. I'm only drawing 3 dimensions, and I've kind of drew it as if the amplitude decays like in some continuous way. It's really a discrete function. But the idea is that, okay, so the amplitude is like the probability is strongly concentrated for the ground state wave function near the exact solution, and it decays in some way away from there. And for most choices of local interaction you can add, whether it's this particular one or other ones that maybe have a sign problem, it'll be localized near there. So if we sort of imagine drawing it, if instead of drawing this hypercube, which is a little harder to draw, if we drew the wave function as a function of, say, a single degree of freedom, just imagining that this hypercube could be written as a one-dimensional space, the ground state wave function will look like this. It'll have some exponential tail. And now, on the other hand, far away on some other corner of the hypercube, there may be some excited state wave function, which would be a low-lying excited state. And now these wave functions are localized in completely different parts of the hypercube. And this one might be almost the same energy of this. If the weights are integer weights, maybe this one at s equals 0 is only energy 1 above. It's almost as good as the ground state. And then when you add on the transverse field, it can easily happen that at no transverse field, this is the ground state. And at small transverse field, this becomes the ground state, and there's a level crossing. And of course, it actually becomes an avoided crossing, and it becomes a very small avoided crossing. And they say, well, really the problem is that there's a localization, that when you add these local perturbations to this thing, the ground state wave function for small values of this perturbation, when this transverse field term is small, is going to be localized near a certain portion of the hypercube, and that's the problem. So I want to talk about the algorithm. I'm going to talk about another algorithm for optimizing this problem, for doing this optimization. And the idea of this algorithm, this is not how I explained it in the paper, but it's how I'm thinking of it now, so I want to talk about it now, is to think about different ways that the wave function could be localized. We have some wave function psi of x. Yeah.
This thing is really localized in the sense of Hamming distance, right?
Yeah. So like the amplitude decay exponentially with the Hamming distance away from there. Yeah. I mean, of course, I can only draw a small cube, so that's why I'm pretending it's one-dimensional. But yeah, so if you want, you could say that this is the Hamming distance from, then it would be sort of a more sensible plot. Yeah, to say like the Hamming distance from the origin, then it decays exponentially. Yeah, sure. So that's a good way to talk about this plot. So it's localized in the Hamming distance.
And that's bad because that means you're not exploring the circuit.
You're not exploring, but also it means that there's one wave function here, and there's another wave function here. And this is the ground state, and this is an excited state. Right. And they have exponential tails that just barely reach each other. So yeah, they can't actually do a level crossing. But if you change the Hamiltonian a little bit here, this energy can go right through that energy up to some exponentially small crossing. And how big is that crossing? It's the ability to tunnel from here to here. Right. You might have to tunnel a distance of order n, because they might be far apart. Yep. And because this all happens at small s, it can happen in an s that's like order, the transverse field that's order like 1 over n too. A very small transverse field. And that's how you get n to the minus n, because you might have an incredibly weak tunneling between things incredibly far apart.
Wait, and you said before that you think making it non-stochastic doesn't help?
Yeah, because the same localization, I think, probably goes on there. I mean, so there's no proofs, but there's good physics arguments, and, So, okay.
It's also relevant that it's not just one other state, right?
It may be many. It may be many. It may be many. Yeah, I'm just.
I think it's known that if there's only a small number of other states, then this does work.
I don't think so, but I don't know. Well, okay. If there's only a small number, then no, you can have trouble with just one or two others. You just depends on how many others that will dictate where the level crossing occurs. It depends how many there are. Depends how many spins are flippable and so on. I'm going to get into stuff related to that. So I want to get into the idea for this algorithm. So this wave function has some norm, right? Psi of x squared. So x will be like the position. And things might be localized in the sense of this L2 norm. That is, almost all the weight of the L2 norm is concentrated near this point. On the other hand, you can imagine that if you looked, it seems like a strange thing to look at, the L1 norm of the wave function, that this might be delocalized. Most of the weight of the L1 norm might be far from this point, even though the wave function itself is localized near here. You could have a large tail. And why is this interesting? Well, suppose we could do some Hamiltonian, not exactly this one, but we can make some weak perturbation that got the wave function to be delocalized in the sense of this L1. That would mean, in fact, it would have a very big L1 norm. If this L1 was delocalized and this L2 was localized, and the norm of this is, some of this is clearly equal to 1. So if this guy is delocalized, then the sum of this might be much bigger than 1. And what is this quantity? Well, if the wave function is all positive, if the wave function is positive everywhere, if psi of x is greater than or equal to 0 everywhere, then this is actually just the inner product of the wave function with a state that I'll call psi plus. That's the maximally polarized state, the state where everybody's polarized in the transverse direction up to, there's like a 2 to the n over 2 factor in front. Oh, so psi plus, let's say psi plus is plus to the tensor product n. Everybody maximally polarized. So it just has the same amplitude on every site. And so there's a 2 to the minus n over 2 in the normalization. So if you take this inner product, you get there. So if we can get this thing delocalized in the L1 norm and get a large L1 norm, that means we can get a large inner product with this state. Significantly larger, perhaps, than the 2 to the minus n over 2. And then that gives us an idea for a quantum algorithm. The idea for a quantum algorithm, let me first think about it in reverse. In reverse is, which of course we can't do, but then we'll run it forwards. Prepare the state in the exact ground state. Of course, we don't know what the ground state is. Do some tweak to the Hamiltonian so that we get to some state which is delocalized and has a large inner product with psi plus. Then measure psi plus, and you'll succeed with a probability much bigger than 2 to the minus n over 2. Much bigger than 2 to the minus n, sorry, probably much bigger than 2 to the minus n. So that then inspires the quantum algorithm of 1, prepare psi plus, 2, now evolve, and I'll explain it more, evolve a short path. And what do I mean by a short path? What I mean is we're going to start with a Hamiltonian whose ground state is not psi plus. Its ground state is going to be this ground state here that's almost this localized one, but not quite, from that delocalized one to just completely h of z. So I'm going to call it from h of 1 to h of 0, where I'm changing notation now. H of 0 is going to be h of z to h of 0, and h of 1 is going to be something else I'll explain. It's going to be a little perturbation of h of z. So you're going to evolve from here to here, and then measure in z basis. Measure in z. And see if you succeed. And so if you didn't have this evolution here, if you just prepared psi plus and measured in z, the probability that you get the correct ground state would be probability 2 to the minus n over 2. So this thing would succeed 2 to the minus n of the, probability would be 2 to the minus n. The amplitude would be 2 to the minus n over 2. Probability of success would be 2 to the minus n. And so then you could apply standard amplitude amplification, basically just doing Grover search, and turn it up into a time 2 to the n over 2 algorithm to find the ground state. That's not very interesting. That's just Grover search again. But if we can make this so it has a larger amplitude, we can speed up. So we will take a time 2 to the n over 2 is Grover, and we'll have a speed up that depends upon a certain overlap. And it will depend upon this overlap here. It will depend upon an overlap between a certain ground state psi 1, or let's say psi 0, 1. It's the 0 for the ground state and 1 to indicate that it's for this Hamiltonian H1, and the state plus squared. Whether we can create a large amplitude, a large inner product between these two states.
Can I ask, the difference between what you wrote on the board and the Adiabatic algorithm is that you're not starting in the ground state?
We're not starting in the ground state. There's going to be actually 3 distinct differences. One is we're not starting in the ground state. So that's sort of the short path thing. That we're not starting the ground state. The second one is we're not going to do this Hamiltonian. We're going to do a different Hamiltonian.
For the H1 to H0.
Yeah. This is going to be a different Hamiltonian. And the third one is that we're going to actually need to do this evolution to ridiculous accuracy. And I'll explain how we do that later. Like the evolution here needs to be done to exponential precision, but that can fortunately be done in polynomial time. So.
An evolution to exponential.
Yeah. So what I want to do is I want to have something that if you just adiabatically evolve, slowly changing the Hamiltonian, you have to worry about like the error, when you run it on a quantum computer. So fortunately, because this will be a very small change in the Hamiltonian, it will be possible to do this up to some error that's exponentially small in n using existing quantum simulation techniques and phase estimation. So I'll skip that, but we'll just take it as granted that we do need to do a very accurate evolution in here, and you can do it.
Sorry to jump ahead, but once you had this algorithm, could you then dequantize it and get a classical algorithm that beat 2 to the n?
No, it's a good question. I mean, I thought about that similarly. I don't know how, and my suspicion is no, that really this is, to be very heuristic, this is actually a use of having a Hamiltonian with no sign problem, that you can get constructive interference from all the different things that happen to create this large L1 inner product. That essentially what's going to happen when I analyze the problem, I'm going to get some random walk, which looks very classical, but I get to add all the amplitudes in a constructive way. So I don't think so, but maybe.
So this could be a super Grover speedup.
Well, it is under an assumption on the density of states. You need an assumption, but it's a fairly loose assumption. Okay, so this is the algorithm. Yeah.
I don't understand. So what's written there is psi plus inner product with the ground state?
With the ground state of this perturbed Hamiltonian that I haven't yet defined.
So what's the difference between, tell me whether there's a difference in speed if I prepare psi plus and I do phase estimation and I measure in that basis of energy.
Actually, that's exactly, okay, yeah, good question, Dorit. That's exactly, in fact, how you wind up doing it to do this to very high accuracy. Because it will turn out, it's sort of funny, this ground state of this H1 will actually be very close to the ground state of H0. So in fact, all you need to do to evolve is you actually, when you cut it down to its simplest, you prepare this, you phase estimate this Hamiltonian, measure that. So that's actually all you need to do, because these two states are almost the same. But the idea is, even though they're almost the same, like maybe there's like a small angle between them, like 45-degree angle between them, their difference is enough to greatly increase the amplitude of this state in the psi plus direction. So yes, actually the full algorithm, can be simplified to just prepare, phase estimate, done. And that's how, and then you do the phase estimation to very high accuracy, using the ability to estimate exponential, exponential accuracy, probability of misestimating using a polynomial number of measurements.
But the secret is how to find the Hamiltonian.
Yeah, so now I need to talk about what Hamiltonian would do. So the whole thing is just about, coming up with a Hamiltonian whose ground state is very close to that one, but has a large overlap with the psi plus. So what is the Hamiltonian I'm going to choose? So here's an eraser. Okay, so I'm going to get a... So I'm going to slightly change the family. So it's going to be h of s is going to be this h of z minus s. So s is this parameter, but we're just going to do s equals 0 or 1, times b, which is a strength of a field. B is positive, times x over n to the k, where k is an integer exponent, okay? And so we're going to choose these two quantities, b and k. And what we need to guarantee, there's going to be a small change in the Hamiltonian from here and here. We don't want there to be a level crossing. Now, if there is no level crossing, which we'll discuss later, and this can happen, then you get a runtime that is going to be O star of 2 to the n over 2, that's the Grover thing, times x, here's your speed up, of minus b over 2 dkn, where little b is, the notation gets kind of unwieldy, and I have not been able to simplify it. The notation is little b is big B over the ground state energy, over the absolute value of the ground state energy. So basically, the bigger you can make this, the more speed up you get. On the other hand, when you make this power k bigger, the less speed up you get. So depends upon how big you can tweak these terms, and you tweak them in such a way that it still runs, but that you don't have a certain bad thing involving level crossing happen. But we can give some guarantees under which that level crossing doesn't happen, much stronger guarantees. So it's a speed up that, and D is that order of whatever we're doing Max-D Lin to. The details don't matter. It's a speed up that depends upon these two parameters. I mean, the details do matter, but don't get caught up in them at the moment.
Wait, these parameters, do they involve things like the number of clusters, the number of disconnected clusters, or?
How do we pick them?
I know you were interested in that subject.
Yeah, we'll get to what those why these parameters are important.
Okay.
They're just, they're parameters to speed up. You can kind of look at it and see that if k got really large, if k was of order n, then this term is basically 0 except when x becomes of order n. So it's basically just a term that projects onto the maximally polarized state if k gets too large. So it becomes uninteresting when k gets too large. This term, though, the bigger we make it, sort of the more effect this transverse field is able to have. So this is the kind of Hamiltonian we study. So I just want to discuss, I don't have too much time, so I want to discuss, I'll get to you in one sec. Two things. One is how one shows this, because this relates to this interesting random walk thing. And then what are the guarantees under which you show this? How do we, what assumptions do we have under h sub z such that this happens? Because we can give specific statements about the density of states hc such that if those hold, then this will happen. So yeah, question?
So what is this Hamiltonian? What is x over n to the k?
So x is sum over I xi over n, okay? So it's just, n is the number of spins, it's just a normalization. It's just this a nice way to normalize it. K is like 3. It's an integer. It's an integer. The bigger k is, the less guarantee of a speed up you get, the less speed up you get, but the fewer assumptions you need to get that speed up, the weaker the assumptions under which you can show that speed up are. So they're parameters you pick.
Should there be 1 over n in both, like in the definition of x and in the term?
No, this right here. Yeah,
How can we get complexity which depends on the ground energy with no shift?
How does it depend on the ground state energy?
No, I'm saying how can we get complexity? You write there b equals large B over epsilon over the ground energy, right?
Yeah. Yeah, we're going to get to that. We're going to get to that. We're going to get to that. Okay. We're going to get to that. Okay. So how do you show this speed up first? Assuming a certain thing holds, how would you show this speed up? Well, I want to analyze the ground state of this Hamiltonian at s equals 1. I want to analyze this ground state. And there's a really nice perturbation theory called, I'm going to mispronounce the French, but Brillouin-Wigner perturbation theory. So this is a really beautiful tool invented by Brillouin-Wigner for studying perturbation theory of Hamiltonians. And most people, you've probably seen if you have a Hamiltonian that's a sum of two terms and one is a perturbation to the other, series for writing down the eigenstates of the perturbed Hamiltonian. And they usually, if you do Rayleigh-Schrödinger, which is the usual series you'll see, they get hideously complicated after the second order. Everyone knows the first order perturbation theory. Everyone knows the second, where it's like the square of the matrix element divided by the energy difference. And then nobody knows the third, except for people who do it specially because it just gets ridiculously complicated. Brillouin-Wigner just stays nice at all orders. It's a very, very nice way of doing it. Now, in this talk, I'm going to assume a unique ground state for h of z. The paper did a unique ground state. I have a manuscript in preparation that removes that assumption. But for simplicity, I will not do that. We'll just assume a unique ground state. But you can remove that assumption. Okay, so you have some Hamiltonian h sub z plus some perturbation v. And you want to study the ground state, the eigenstates of this. So what you do is you write down, and let's put an S in front. So S is like a strength of perturbation. You're going to define the ground state as in a series of this. So of course, and we're going to write the ground state as phi rather than psi. And the reason is that I'm going to save psi for things that are normalized to have norm 1, and phi is going to be normalized a little bit differently. Phi is going to be the ground state of this, but normalized so that its inner product with the original state is 1, but its norm itself will be bigger than 1. That's what it is. Okay, so what is phi? So phi, well, to 0th order is just psi, right? So to next order, I'm probably going to get all the signs wrong here, but you can check the paper for the signs. So to next order, you have something that's like a sum over. Let me say that h sub z has eigenstates psi u. U will index different eigenstates with energy EU, E sub u. So psi 0 will be the ground state of h sub z. Psi 1, psi 2, psi 3 will just be excited states with different energies. So phi will be psi 0 plus a sum over u not equal to 0, s v psi u over EU minus E naught. And I probably have the sign wrong there. I think it's probably a minus. So that's the same as the usual first order perturbation theory, right? Perturbation theory, matrix element to excited state divided by an energy difference. Next order, plus sum over U and V, both not the ground state, s squared. Oh, sorry, this v is, sorry, let me fix that up. Psi u times the matrix element, psi u v psi 0. So the matrix element from the ground state to an excited state, and then you put the ground state in, the excited state in there. So it'll be a sum of s squared psi u over EU minus E0, EV minus E0, and then psi u, v, psi v, psi v, v, psi 0, and so on. This one stays simple at all orders. So every order in the perturbation series has the ground state, and then matrix element to one excited state, or one excited state to the next excited state. At third order, it will be psi 0 to psi v, psi v to psi 0 to psi v, psi w to psi u, and so on. A sequence of energy denominators. That's it, except, let me just correct it. This E0 is not the ground state energy. This is, I'll write it as E0 comma 1. It's the ground state energy of the perturbed problem. That's what makes the perturbation theory ridiculously simpler. If you keep this as the ground state energy of the unperturbed problem, which is the usual way that the perturbation series is expressed, and you try to normalize the state to 1, then beyond this order, everything gets very complicated. But if you make this the energy of the perturbed problem, and you normalize it this way, then it just stays simple at all orders. And you can analyze this series pretty nicely, because what happens is when this v is this x over n to the k, x over n to the k just takes k random spins and flips them. You can flip the same spin twice, that is too.
That's the energy of the perturbed problem for what order?
The ground, the exact, no. This, yes, the exact energy of the perturbed problem. If you try to expand this in powers of s, then you can get a full, if you expand E0 comma 1 in powers of s, then you can get a series where everything's just expressed. But this is the exact energy of the perturbed problem. So that's a weird perturbation series. At s equals 1, this is correct. So let me just in general put E0 comma s. So this will then hold for any s, that it's defined self-consistently. So now I start with the ground state. This just flips k random spins and gives me an excited state. This says take the ground state, flip k random spins, flip another k random spins, get an excited state, and so on and so on and so on. So what I get is a sum of states. All these states are going to come in with positive coefficients. So I can easily compute their inner product with the psi plus, because their inner product with the psi plus is just this matrix element. The inner product of all these states with psi plus is just 2 minus n over 2, independent of which state it is. So I can easily compute the inner product of this state with psi plus. The only tricky thing is to compute this energy denominator. But there's a nice thing, that if you take the initial state that has energy E naught, and this is, one of you two asked the question, how can the complexity depend on E naught? Take an initial state that has energy E naught, flip k random spins, the energy will typically go from E naught to E naught times like 1 minus k over n, because you flipped a certain fraction. Actually dk over n, because d spins can appear in each one. And so you can estimate that this changes by, this energy difference is really E naught times k over n. Then you get it twice. Now you might worry, oh, these are correlated random variables. This is a random variable. You're doing a random walk. You're randomly walking and measuring a product of energy differences. But actually, this is a simple calculation that doesn't matter how they're correlated. That this energy, that you can effectively take this first energy difference and substitute k over n, and this substitute k over n and 2k over n, because you've flipped it twice. K over n, 2k over n, 3k over n for the third order, and so on. So it's just a nice little fact about random variables. Doesn't matter how they're correlated, that when you compute this inverse of products, you get that. And so you're going to get some series when you want to compute its overlap with the ground state, when you want to compute its overlap with psi plus. So then all these things become 2 to the n over 2, where this becomes like k over n, this becomes k over n and 2k over n, and then next row you get k over n, 2k over n, and 3k over n. And if you look at it, you realize it looks a lot like the series expansion of an exponential, because you have this powers of s in the numerator, you have powers of k over n to the denominator, and you get 1 times 2, 1 times 2 times 3, so you get a factorial in the denominator. So you resum it all, and you get that speed up over there. So this gets to Scott's question, like how does the speed up come? There are all these paths, but somehow they all constructively give a contribution to the overlap. So that's why that I think is how the algorithm works. So the last thing I'll mention, okay, under what circumstances can we show this? When can we show that this works? We can show that this works as long as, there's a few assumptions for this series the series is always convergent in fact, if this ground state energy is put in as the ground state energy. But you need to show that the ground state energy didn't shift too much, that the E0, 1 is actually still pretty close to E0 and didn't change too much. And you also need to show, to do that second step of phase estimation in the algorithm, like start with the state and phase estimate that you're in a ground state, you need a gap to stay open to measure that you're in a ground state. So you need a gap of some Hamiltonian to stay open. You need that when I add this weak perturbation to it, that really the initial Hamiltonian, I was assuming initially we had a unique ground state, so it had a gap of 1 between the ground state and the first excited state. As I said, that can be removed, but for simplicity, let's keep that on. Then when you add this small perturbation, the energy changed only a little bit, that the gap stayed close to 1. And here, what we should think is, OK, can we make a state of this Hamiltonian that's got, initially the Hamiltonian had some energy E0, and then a whole bunch of states with energy E0 plus 1, and then more excited states at higher energy, so on. We want to ask, when we add this perturbation on, what happens to this gap? How much can this gap change? And in order for this gap to change, it has to be the case that looking just in the subspace span perpendicular to E0, we can find some state that has an expectation value for this Hamiltonian with energy close to E0, right? So we want to ask, can this gap close? Can it be the case that when we turn on S that suddenly, there's actually a whole bunch of states down there, that one of these states came down from here? In order for that to happen, it has to be the case that if we look at this Hamiltonian projected into the space orthogonal to E0, that you can get a state with energy close to E0. So you have to be able to get an expectation value of this term that's close to 1. You have to be able to get some state that has some state psi, I'll call it xi, some state xi, such that expectation b x over n to the k is like of order 1, or say a half, has to be at least some constant. And also expectation hz of the state xi isn't too big either. You have to have a state, you have to be able to form some state that has a large enough expectation value for this guy to compensate the fact that it's made out of excited states for that guy. And this is where the high power of k comes in. Because the only way, you may worry that, this is an expectation of a power of k. For simplicity, there's technical steps to get around it. Imagine we were just thinking about taking the expectation value outside of the power.
Is this also where the requirement for large L1 norm comes in?
No. This isn't. This is the ability for the algorithm to succeed, and this gets down to like how many perturbed states you need for it to succeed.
How do you connect this to this requirement of the large L1 norm?
Well, the large L1 norm came from this perturbation series. So this is to show that the perturbation series works, and to show that we can successfully measure whether we're in the ground state. So as I see it, they're two distinct things. That the large L1 norm came from this series.
Where did it come from? This?
Oh, well, so I'm summing up this series. And when I sum up this series to get the inner product, every single one of these terms contributes some constant, right? Some quantity that's independent of what this final state u is. I can just replace this psi u with 2 to the minus n over 2. And then I sum it up, and the question is, like, can I get a large contribution from the higher order terms of the series? If so, then I get a large L1 norm.
So Matt, is it the case that, these things sum up, and that has to do with, that's related to the fact that there's no sign problem?
Yes. That's where it tries to take advantage of it, that there's no sign problem.
Is that not counted? Usually we think no sign problem, those are the easy ones.
Right, so now I think that's actually a good thing here. That's actually a good thing, because it's like there's many trajectories and they're all interfering constructively. And how would you, the whole art of a quantum algorithm is to make many trajectories somehow all do the same thing useful. And so there's one way to do it. There's a lot of ways to do it, but one way to do it is to make every trajectory have the same sign.
Does this say anything to the intuition usually that you can, if there's no sign problem, you can simulate with quantum Monte Carlo?
Right, well, so of course that doesn't say anything against that, because we're only going for a speed up that's, from 2 to the n to 2 to the n some lower exponent, right? So, if you go from, or 2 to the n over 2 to 2 to the n over 2 times some lower exponent. So if you were able to speed up, that doesn't imply that there couldn't be a further polynomial classical speed up. We're going at best for a polynomial speed up over Grover, at best. So it wouldn't into.
Couldn't you write all this in terms of?
Yeah, you could sample all this, but most optimistically, it's not even clear whether you could efficiently sample it, and I think you really gain from the interference. But most optimistically, when you sampled it, you still would have a polynomial slowdown in your sampling, which then is no contradiction, because this is only going for a polynomial speed up.
For what setting of these parameters do you get the largest speed up over the best known classical algorithm?
Well, as I said, any setting is a speed up over the classical algorithm, because the fastest classical algorithm is 2 to the n.
I said the largest.
Okay, so that's what I want to get to. What's the what conditions can we put on these parameters?
Right.
And that gets to the last thing I want to talk about, Log-Sobolev inequality.
All right, good.
So in order for the thing to fail, there has to basically be some, when we turn on this perturbation, the gap between the ground state and the excited state has to become small, essentially so that we can no longer phase estimate which state we're in. That's when the problem arises. But in order for that to happen, there has to be some state formed out of excited states that has energy close to what the ground state energy is. So it has to be gaining in energy from this term because it paid a price here. Now, so that means it has a large expectation value for this term. Now, technically, it's a large expectation value for a power of k. Just to simplify some of the technical steps, let's pretend that it's really that if you take the expectation value of x over n, it's a large expectation value for the kth power of that. We'll change the power of the expectation value of the kth power for the kth power of the expectation. There are technical steps to get around that, but we'll just pretend that. So if k is 3, say k is 3, then if x is square root of n, if the expectation value of x in the wave function is, say, square root of n, which is actually quite a polarized state, yeah? It's got a pretty strong polarization, then this would be like a 1 over n to the 3/2 thing. So even if b is polynomially big, b could be as big as n to the 3/2, so that depends upon how big the ground state energy is. And this term would still give only a small contribution. So you need to have actually states with a very large expectation value of x in order to get a large expectation value of this. And the bigger the k is, the bigger I can make that expectation value of x needs to be. If k is 100, then even if the state has an expectation value of x that's like n to the 98 over 100, this still gives only a fairly small contribution. It needs to really start having like powers of x that are almost fully polarized, x very close to 1. And so there's a nice inequality. There's a whole literature of this inequality called Log-Sobolev inequality. And the funny thing is when I tried to read it at first, I went to a talk about the conference about this years ago, and I didn't understand anything. But I realized it actually means something very simple in quantum mechanical terms. The type form of the Log-Sobolev inequality is this. You take a state psi that's a pure state, and someone tells you you have 2 tasks. You are given a fixed x polarization of that state, okay? And you want to minimize its entropy when it's measured in the computational basis. How do you do this? Someone says, okay, it should have an expectation value of this capital X that's exactly equal to da, 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 and I want to have as little entropy as possible in the x basis. How do you do it?
Fixed x polarization means fixed inner product with the plus.
With first, fixed expectation value of x. Just the expectation value of x is fixed. The total expectation value of x is fixed. And you want to minimize its entropy in the computational basis. How do you do it? The answer is, and this is the Log-Sobolev inequality when put in these terms, is write down a product state where every qubit is polarized somewhere in the xz plane in such a way that that the total x polarization is right. So when each qubit is fully polarized in the x direction, then, and that's the tight answer, when each qubit is fully polarized in the x direction, then the entropy in the computational basis is maximum. As you start to make each qubit get more polarized into the z direction and less in the x direction, you get less x entropy, but more z entropy. And this gives a relation then between a large x expectation value and a large entropy of the state. So the only way you can start to generate these states is if you have also an enormous number of low-lying states. So you can make it such that if I pick k to be like 99, which would still beat a classical algorithm, the only way it would fail is if there is something like there are states that are very highly polarized, like n to the 98 over 99 polarized, which would mean that there's sort of 2 to the n to the 98 over 99 states with energy within like a constant of the ground state. So not just like 1 or 2 states down there, but an enormous number, and you can tune how many are in there.
And that's not fitting also the cases where the classical algorithms fail?
Okay, so as far as I know, yeah, I mean, I've been trying to study the classical literature to learn more about this. There are some, second paper coming out, there's some obvious classical speedups you can do when you have huge numbers of low-lying states. As far as I can tell, these give you more in the cases where it does, but I'm not an expert on it, and so if someone can tell me more, I'd like to know more. So anyway, I'm pretty much way over time now, but so let me just conclude. So the things I want to emphasize: this exact optimization is hard. Classically, very little is known about exact algorithms, but there are very good heuristics in practice. Quantumly, I don't think there are good heuristics, and I think the trouble is this localization. But I think we can kind of turn it around, and we can take advantage of these tails of the localization, and we can take advantage of no sign problem to give a constructive interference and get a speed up. And so this is the whole idea of it, to get a constructive interference and get a speed up from tails of the wave function. When you only slightly change the Hamiltonian, the gap doesn't close. And there's really three ideas in the algorithm. One idea is short path. You don't try and follow a large path. You just try and perturb a little bit around it. You need to very accurately follow the ground state evolution using this high accuracy phase estimation, as Dorit asked. And you use this power of x over n, which allows you to prove some results. And similarly, in the analysis of it, there's really two key ideas in the analysis. One idea is this Brillouin-Wigner perturbation theory, which allows you to express it in terms of random walk and makes clear why having no sign problem can be an advantage, because you can get a summing up of all these terms in this series. And this Log-Sobolev inequality, which gives you a way of understanding that, well, the only way this algorithm fails, and so you can express it in terms of a theorem that either this algorithm finds the ground state in this time, or the problem has this number of states with this energy at most that, and you can make those guarantees look rather extravagant in terms of it must have an enormous number of low-lying states with energy at most this. And yeah, I would be very interested to learn more about what's known classically. So let me stop here.
Further questions?
So how you studied this in detail for a specific problem like this HC? So, can you think of it more generally? Is it saying something about, okay, the Adiabatic algorithm, we try to do it, we don't understand the gaps along the path, and you're saying, well, that's not the way to think about it. You can understand the gaps. Yeah, you can use perturbation theory, and so let's find ways.
Yeah. So you're right. So there's exactly one case in this whole talk where I used that it was Max-D Lin too. Okay, one case, which is that when you analyze these energy denominators, you say that, well, if you have a Max-D Lin 2 instance and you flip some randomly chosen fraction of the variables, you can estimate how the average energy changes. You can say that if I flip k of the variables, the expectation value of the energy after flipping them is if I have a state with a given energy, afterwards it's like 1 minus k over n of that energy, or actually 1 minus dk over n of that energy. For more general problems, it can change in much more dramatic ways, but maybe some other guarantee can be made. So somehow there's something about the landscape of this Max-D Lin 2 that if there is a minimum, I mean, any algorithm that tries to get a speed up has to assume that the landscape of this HZ is not like a golf course, that it's not that HZ is completely flat except there's one answer somewhere. So you have to exploit something about it. And somehow this Max-D Lin 2 has one useful thing, which is that if you start at low energy and you flip a bunch of variables, the energy doesn't change too much in some way. And you can control much better how that happens than for other problems. I mean, of course, there will still be some guarantees as to how the energy changes, but I don't know as strong ones. So that's where it's used. But yeah, you could analyze it for others.
Okay, so it sounds like you're saying either the algorithm works or there are a lot of low-lying states.
Yes.
So can't you get an unconditional algorithm then which says no matter what you'll get a pretty good solution and then
Yes. So, okay, good. Yeah, again, a good question. So I have something about that in my paper that, you can make a hybrid algorithm. You can say, we run this algorithm, and at the same time, we also just run a straightforward Grover search to try and find a low-lying state. And you can then make some statement about either you find an exact solution in this time, or within this time, you find a solution of this quality. And again, as far as I can tell, I don't see a classical one that's as good. And the two things that I saw are, one is, getting back to the question about Schoning's algorithm, there's a modification of Schoning's algorithm to deal with finding approximate solutions. And I didn't see anything getting as quite as good. And there's some other work on hybrid algorithms for certain problems of this form. And depends what kind of solution you're going for. In certain regimes, they do better when you're asking for like pretty good approximate solutions. But when you start asking about, I want a solution that's within, energy 1 of the ground state or energy 2 of the ground state, where the ground state energy might be n or n to the 3/2 or n squared or something, then I don't see a classical one as good. But again, I'm not an expert in that field. I mean, it's just what I can piece together.
And what happens if instead of modifying, doing the hybrid, would this algorithm by itself, with slight modification, give you those?
Okay, it's a good question. Yeah, I mean, you may ask like, well, if this fails, I mean, it does still give you a state, and it will give you a state that's a good question. I'm not sure. I mean, one thing that's interesting is if it fails, it will identify a state that's sort of like this. That's one thing you can do is you could run it, and sometimes you could go measure in the z basis and get your state. But sometimes, if you felt like you could run it and measure in the x basis, just for fun, and you'll see like, oh, these are the spins that got polarized. And so what I've been thinking is that may mean that you can identify, a large basin of flippable spins. Like, oh, this, this fraction of spins, which is actually some enormous fraction of the total number of spins. By the way, you could take like k to be log n, and that would give an algorithm that's still 2 to the n, but is 2 to the n minus, or 2 to the n over 2 minus n over log n, and I don't know how to do that classically either. Then it would require that, in fact, not only that there's like half the spins are flippable. So you could get something which will identify, oh yeah, actually, here's a solution where these spins are fixed, and all these ones can essentially be chosen at random, and you still get a very low energy state, and we'll find you that basin. So I don't know what, exactly what that's useful for, but I've been, so I have something in preparation which extracts some sort of fairly simple stuff from it, but I expect that more can be extracted, that you may be able to say that, yeah, problems where this fails, like really you can pin down a lot about the state, but I don't know. I would like to talk about it.
Scott, you want something?
All right, yeah. So it sounds like you might need some numerics to work this out, but like make the most optimistic, assumptions you want. Do you think you can get a cubic speed up over the best classical algorithm, or like give me an estimate?
Okay, yeah, no, that's a good question. All right, I'm forgetting this off the top of my head. I have 2 different things I could tell you in terms of 2 different problems. One is you can look at a completely random choice of this h sub z, where the variables are chosen plus minus 1, and you just look at the case d equals 2. You could also look at higher d too. If the weights are chosen Gaussian, a lot is known about that problem. In fact, there's even rigorous results on what the typical density of states is. And then, yeah, you can get an additional speed up, and I don't, off the top of my head, know exactly what the numbers will be, but let's just say roughly you'll be in the ballpark from maybe going quadratic to cubic or something around there, speed up over classical. And then another fun toy problem you can study, and again, I don't know what the number are. I just ran this one on my laptop for fun. You can ask yourself, I mean, this is all regime in which you can prove things. And you can ask yourself, well, yeah, could I push it even a little further about the low energy density? You could take d equals 1, so it's just a linear function, and just polarize all the spins in the z direction for h sub z, and study that toy problem, where it's just all the spins are polarized, and you get some other polynomial speed up in it. I mean, it's obvious you should get a polynomial speed up because you can do that one with the adiabatic. But you might want to just ask, well, how much can we do in this case? And there is a limit to how much you can do if k is chosen bigger than 1, because you do encounter certain level curves, but you get some other polynomial. And again, I don't remember what that polynomial is, but I intend to study more. Yeah.
Matt, isn't this a black box algorithm?
That's what. Yeah.
Yeah, I mean, I just analyzed one case, but I would hope that maybe there's some more.
So how can you expect a better than Grover's?
Oh, sorry. When you said black box, I thought you meant that it's a sort of a family of items we can plug in better HZ. No, because I use something very specific about HZ. I use something very specific, which is that if you flip a bunch of random spins, the energy can't change too much.
This is in the analysis, but in the algorithm, isn't this a black box?
Yeah, but if that didn't hold, there would be no way to say that this thing was large.
But the oracle is not just Boolean. It's telling you.
Sorry?
Every algorithm is black box. It just doesn't work for certain things, right?
So let me put it this way, okay? We analyze this term here, okay? Say we have some initial energy that's E naught of the ground state, okay? So it'll be some large energy that we can get some very large, that's the ground state energy. When you do this first flip, you're taking the ground state and you're flipping k over n of the spin, some very small fraction. So you have to be left with an energy close to the ground state. So this energy denominator can't be too big because it's only the fraction of spins that you flip that enter in there. But if you had totally a black box, this energy denominator could be as big as E naught. It can be much, much bigger. And that's the difference. That's how it enters. You're really exploiting the fact this energy denominator difference is exactly where what enters in is that the landscape of this problem is not a golf course. It's it's got some cones or something, some mountain lakes.
Matt.